Hello everybody. So thank you very much for the invitation. So actually, I plan to talk about two different but related topics, and both of them started during or with a discussion with crypto people. We had a project that involved a lot of cryptographers, and we had forth and back just understanding each other. So the first one, the C-coordinate channels with continuous alphabets and infinite dimensional output Hilbert spaces, was initiated by through a discussion with Juliane Kremer. So she explained this physical side attacks, and one particular attack was photonic emission analysis. So where the people detect photons transmitted by transistors and then recover the secret keys. So and then we just understood it is actually a CQ, the classical input quantum output channel, which operates on bosonic systems. So it's well-known notion in quantum information theory. Okay. The second part was this branch of the channel that goes to the eavesdropper. So the cryptographers always ask, how do you know this channel? So if you think of wireless channels, so you actually don't know this channel because the eavesdropper doesn't cooperate with you, right? The third question that they have is secrecy criterion. So if you give them some mutual information, they don't understand this. So they want something like, give me a class of attacks and give me some quantification how your schemes protects against the class of attacks. So that was the bulk motivation for this first part. And for the second part, so I'm going to additive noise channels. And the question was posed by Stefan Katzenbeißer and Felix Clement from University of Passau. They were interested in secure multi-party computation. So it's classic topic in cryptography. So it operates on discrete sets. We at HHI work a lot with in the analog domain, so analog signal processing. And the question was, is there something like secure multi-party computation in the analog domain? So and that's where it popped off. We have this over-the-air computation. So basically, if you have additive MAC with additive noise, so superposition principle just computes some of the inputs. So that's something you can use to compute the functions over the air. So and the question was, so can we do some tricks like secure multi-party communication in computation in this analog domain? So and then we had this discussion, and we could link this to lattice coding, and so somehow that was sort of the conclusion of this discussion. So let's go dive in. So this is how it started with this classical quantum channels with Juliane. She introduced us to this paper by Ferrino and Hlavac from the AIS Blinked, introducing the optical side channel. So, and the whole paper can be explained in this quotation here. So the basic idea behind the channel is simple. Each time a transistor or an integrated circuit change state, there are a few photons emitted. Bang. So, and that's a resolution in space and time. So you get like a movie, right? So if you detect these photons, you get a movie, you know how your device operates. And with some data analysis tricks, you can read out the key. So the objection was, that's complicated. So that's horribly complicated. Actually, they had to borrow equipment or to use equipment of French space agency at that time. So it was really, really expensive and horrible. And then Juliane enters the stage. So that's title of a summary of her PhD thesis. So where they have shown that this complexity is not really high. So the technology developed, and so they performed the same experiment. So that's the snapshot of the movie they get to read out the keys. And we discussed a little bit further. So and then we understood that actually that's from the information theory perspective, this is a channel with classical input and quantum output, and the output are bosonic systems, photons. Right, so we wrote a model. So that's the usual wiretap model. We just assume that the continuous, that the alphabets are continuous and that Hilbert space is infinite dimensional. So now security or secrecy measure. So we decided to use the semantic security. So because it's well established in cryptography, and there's adapted version for wiretap channels, so it's easy to explain. So we have a set of messages, and the goal of the attacker is just to take a partition of the message set and try to decide whether the message sent is in a partition element or not. So, and every partition is admissible here. So examples here, if you want to recover the message exactly, so it's just partition consisting of singletons. Or if you want to check whether the first bit in your message is 0 or 1, so then you have 2-element partition like here, right? So how do you cast this into a formula, which looks really horrible? So that's the advantage, semantic security advantage, but you can understand it very easily. So the last term here is just the optimal guess. So if you assume that you know the distribution of the messages, you know your partition, you do your best guess. And the first part, this first part here, that looks terrible, is you have a partition, you have a quantum observable attached to this partition, you perform the measurement that gives you a decision rule, and then you optimize over your measurement. So the optimal decision rule for catching this partition element. And then you take the maximum over all partitions and all distributions of possible distributions of the messages. So it's operationally well defined. So these are the attacks under consideration. Okay, so and that's the reference to the paper that adapted this classic semantic security definition to this wiretap channel realm. So now time for a little review of prior work. So there's a lot of papers, really nice papers. I cannot list them all. So just a little selection starting with finite dimensional case and then infinite dimensional work. And one interesting point are the references 1 and 2. So the first one is by Igor Bjelaković, and the second one is by Chai, Winter, and Young. So they state their results for strong secrecy, but if you look at the proofs, what they actually prove is semantic security, and it's 12 years or 14 years before, or 10 years before this definition was given. So it's incarnation of distinguishing secrecy, which is equivalent to the semantic security up to constant factors or something like that. Okay, so, and then there's some work by Christian and Moritz, who is here, and Holger, how to convert codes for strong secrecy into semantic secrecy, and to take some constructions in the infinite dimension. So now the results are not surprising. So that's the usual wiretap stuff, that you get some rate bounds, bound on rate of this shape, and then you get average error exponentially small, and you get the advantage exponentially small. Actually, we have some sort of finite block length result, which looks nasty. I cannot put it on the slide, so that's the civilized version of the result. So, but I would like to spotlight 1 or 2 points in the proof, which address some questions we had initially. So obviously, this proofs by Bjelaković, Chai, Winter, and Young, they rely on this Alsfeder-Winter concentration bounds for matrices, random matrices, and they're dimension dependent. So if you go to infinite dimension, and you want some concentration or some finite block length bound, you have to do it in a different way. So you need some dimension independent stuff. Okay. So that's a very sketchy proof sketch. So you take the usual multi-coding book, and you know you can separate the communication part, legitimate communication part, and the secrecy part, which is just resolvability results. So you take this average, so you fix your message and take these randomization parameters L. You have these constraints, and now it starts. So what we have here, we have a function of independent random variables, and that calls for Mr. McDiarmid. So that's one of the most famous dimension-independent inequalities. And if you have this bound on the expectation value, so you end up with this version here. So one point to remark here is this inequality doesn't care for probability distributions or for probability measures. So what you need to apply it is this finite bounded differences condition, which is sort of Lipschitz condition with respect to Hamming distance. So it's modeling requirement, right? So you don't have to care about probability distributions and stuff. It doesn't matter what these channels are. It doesn't matter what the distributions of these code words are. You just care about this Lipschitzness with respect to Hamming distance, right? So this answers initially the question, what can I say about assumptions on the knowledge of the channel to eavesdropper? So this opens the path to answer this question. So we get rid of the strong dependencies on channels and distributions, right? So it's not worked out. Maybe at some point I will work it out with somebody else. Okay. So now the question is, how do we get this expectation value small, right? So and there's another trick, which is well known if you look in probability theory or in stochastic processes books and look up this theory of empirical processes. Sometimes people call it Glivenko-Cantelli theory. Sometimes people call it uniform law of large numbers. So that's the device that drives statistical machine learning, right? So if you use some adapted form of this, you can bound this expectation value here. By these expressions, we can work further to get them small, right? The point here that's hidden, that's in the proof, how this works, these trace class operators, they have a dual space. These are the bounded operators. So I can represent this norm here as a supremum of certain functions, trace, bounded operator under condition. And then it turns out that the symmetrization process is exactly the Rademacher complexity of this class of functions. And then you go rolling with this Rademacher complexity bounding techniques, and then you end up here. So it works for arbitrary alphabets in arbitrary dimensions, infinite dimensional spaces and stuff like this. So that's the main point. So you get a lot of measurability issues and stuff like this. So it took us a lot of time to sort this out, but that's the main idea of the security proof. McDiarmid and symmetrization to get this inequality on top done. Okay. So that's example. So we motivated this with some quantum optics problems. We have a cascaded beam splitter. We took some parameters from ITU documents on free space communications. So how many photons are undetected? So that's garbage, that's lost. And how to design the other parameters. So one input is vacuum. The Other input is some coherent state, and here's also vacuum. They are mixed up, and then a thermal noise applies, and we get a legitimate output and the eavesdropper's output. So what can we do? So if we do numerical calculation, we can solve these problems. There are some libraries in Python which can deal with this. So we have here different communications rates, R, from 0.3 to 0.44. We have on this y-axis, we have this semantic security advantage, and we have the block length here. So, and then you can see how it goes down. So if we evaluate these nasty exponents that we had, and numerically we get such course. So you can turn it around to fix other parameters and look at the rest, and then you get similar diagrams here, right? So that's how the rate, how the block length grows with rate if you fix the decoding error and the semantic security advantage and stuff like this. Okay, so I will stop here because I changed the topic. So are there questions or comments so far? Yeah? Yeah. You lost me in the meantime, and I woke up again when you said Rademacher complexity. Okay, then let's go back to Rademacher complexity. Okay, so let's say we have something like 1 over m, and then this dxi minus some expectation of this dx1. So this is the trace norm. So by this duality results for Banach spaces. So this can be represented. So let's say that it has the trace norm less or equal than 1, just for simplicity. So you can write it as a supremum over all operators in your BH, such that the operator norm is less or equal than 1. And then you have trace 1 over m sum, so that's I, trace a dxi minus, you can swap it. So, and that's, these are your functions. And then you do the usual symmetrization trick with this. So you take the ghost sample and represent, so sample which is independent of these xi's, but has the same distribution. So you represent this expectation in the same way. We have expectation in front. We represent as expectation of such terms, and then you insert this Rademacher random vector and do the symmetrization trick, and then you end up exactly in these estimates from empirical processes, and then you go back to the norms again, and then you get this. Yeah. Are there more questions? So I have 4 minutes left. Yeah. Yes, exactly. So that's one of the points. This is the same machinery, exactly the same machinery as we use for statistical learning. So maybe there's a way to make it rigorous. These all constructions of practical codes, secure codes via learning, but to derive statistical learning guarantees just by this connection. Maybe, I don't know. Plus minus one random variable. Yeah. Okay, so are there more questions? Skip quantum optics. Okay, so it's not that much time left. It's already air computation. The idea is that you use the superposition properties of the wireless channel. So you get addition for free in there. So the traditional approach would be you take all this bunch of data, you source code them, you channel code them, you transmit them to receiver, and the receiver computes the average value. So that's the overkill if you have many sensors, right? So, and here you essentially only transmitted data that is needed for the transmission, right? So we did some work for this with Matthias Frey, where we could compute such nomographic functions under certain assumptions. So this class of functions includes obviously k linear functions, p norms, so you can take these linear functions and apply a Hölder continuous function on that, and we could do this. We could do this for large class of additive max with correlated additive noise and correlated fading. So we just assume that the fading and noise are sub-Gaussian processes with arbitrary correlation. Just performance bounds without secrecy. So, and for including privacy and secrecy constraints, which are similar to multi-party secure computation, is like this. This is the reliability criterion. This is the estimate of the function you want to compute. That's the original function. You want a uniform bound on the probability. So for privacy, you want to convey the function value to the receiver, but you don't want to convey the input data S1 to Sk. So, and that's the point in this privacy definition. So if you only have this U and you have consider the distribution of your inputs, so then they don't depend on the input data. And for the secrecy, so that's this bad guy here, even we can give him or her data without noise if he or she doesn't have this U and U1 to UK, so that the distributions doesn't depend on the data. So that these are the definitions. How do we do this? We just took these construction A random lattices, and then used as keys the randomization over Voronoi cells for each user. And as a key for the receiver, you take the modulo sum of these randomizations. So then you see it's pretty easy to see that it's secure and private. What's big deal to show is that it's reliable. So that's the difficult part here. So the results, so these are pre-processing, post-processing, I skipped this. So the results are, this scheme is secret and private, and you get this estimation error, you get it controlled exponentially. So yeah, so that's, there are some challenges. I will stop here. Thank you very much.
Yeah, thank you very much for the talk. And I think there is time for questions. So,
okay, thank you for the interesting talk. My question may be about the first part. As far as I understand, your motivation is breaking the symmetric cryptography, right? Like AES.
No. It's just we try to understand
side channels. Yes.
We just try to understand each other. So when the crypto people were talking about physical attacks, so they described it in a different language, and after a couple of meetings, we understood what's the common ground. And the common ground for this particular type of side channels, these are just quantum channels that have classical input and bosonic output. Mm-hmm. That's it. And that was the motivation just for modeling this and trying to understand it in information theoretic way, and to try to collect or to develop mathematics that allows us to deal with such infinite continuous alphabet systems.
Yes, I understood this mathematical problem. My question was about your original very first slides. As far as I remember, the problem was that breaking side channels for classical cryptographic solutions. Or am I wrong?
Yeah.
And in your mathematical formulation, this classical encryption is not included, but maybe it's more difficult to break system which is additionally classically encrypted. So what do I mean? So you can see the problem like Alice sends a message to Bob, and there is a quantum side channel. Yes, I understand. She sends classical message and a side channel to Bob.
Yeah.
But since she sends not the open message, but encrypted message, maybe it's additional layers of security.
It's different layer of security. It's different layer of security because we departed from this a little bit from this original cryptographic problem where you attack security chips, right? So that's just a little bit generalized to other hardware.
Mm-hmm.
So the focus is not anymore on this particular problems we started with. So that happens with every transistor.
Yes.
And the difference here. So I'm not sure how to relate this type of attacks to many of the attacks or attack scenarios we consider in the cryptography. So it was important for me that we have definition of security, which has clearly defined class of attacks.
Mm-hmm.
And I can quantify this.
Yes, I think I understand what you tell.
Yeah.
My question is that one situation when Alice sends a message, so standard wiretap channel scenario, and another situation when yes, there is Alice uses this wiretap channel, but she sends encrypted message. So yes, this information partially is leaked to Eve, but it's encrypted, and maybe Eve gets less information in the scenario with encrypted. Sending encrypted message by the wiretap channel. Then in the scenario, the standard scenario, when she sends the message itself, not encrypted. So maybe, what do you think? Maybe it's also interesting to consider interrelation when we use encryption and side channel, and how these two levels of security, physical level and encryption.
Definitely. You're right.
Okay, thank you. But nobody considered yet.
No. It's something I discussed a couple of times with Janis Nutzel. He attended on Monday. So, and that's something that we have on our to-do list.
Mm-hmm. Okay, thank you.
No, so. Yeah, I'm always a little bit hesitant. We had in the old times, we had this leakages defined by equivocation rates where people told, so that's informationally provably secure. But if you try to write down the attack scenarios, and then you can find pretty much very fast, even for strong secrecy, that the protection is very limited. So that's the reason why I stick to this ugly definition, because it's clear. It's clear. So that's the type of attacks I consider right now, and we can consider other attacks and consider relation to encryption. So how does it increase or decrease the security, whatever?
Yeah. Thank you, and all the other speakers again.